Hello, sorry I'm not able to be here today. I wanted to pick up where we left off yesterday. We have been learning what the values of a and d in an equation, whether we pick a parabola or a square root function, our radical function, or our rational function. We had practiced taking our general function notation, seeing the a value that was asked of us, the value we were to multiply in front of each of our parent functions. And then we discovered, using graphing technology, what occurred when we put a 3 in front of our radical graph, when we put a quarter in front of our radical graph. And we were able to conclude that these had a vertical effect, that my coordinates, perhaps if we take a look at my square root function here, that my coordinate over 9 up 3 was tripled up to up 12 when we had a 3 in front in my A position. And when I had a quarter in front of the A position, that up 3 went to a quarter of what it was. And a quarter times 3 went to 3/4. And so we concluded that an A value was responsible for a vertical stretch factor, which could be an expansion or a compression. And when we had a value of a that was bigger than 1, we could count on our graph expanding vertically. When we had a value of a that was lower than 1 but still positive, we compressed vertically by that factor of a. We talked about the fact that our vertical coordinate, our up-down coordinate, is our y coordinate, and so it's the one that gets affected. We go over 9, not up 3. We still go over 9, but we affect that vertical coordinate, the y value, by multiplying it by whatever is in that A position. We had just got started discovering the effect of multiplying inside our function. And we took a look at our quadratic function, and we discovered that we had a very different effect. When we put a 3 inside our square, we actually had our parent graph be compressed horizontally towards the y-axis by a factor of a third. So every one of our horizontal distances, instead of being over by 3, I went only over by 1 horizontally. We also put a quarter inside my square, and we found out that, those values that were over 3 were still up 9, but they were no longer over 3. They were over 4 times as big horizontally. And so we got a horizontal expansion by 4. And so now that we've reviewed where we were, let's continue on applying our knowledge, discovering whether it has the same effect for our 2 new parent graphs, our radical function and our rational function. So here is our base graph of our function that is taking the square root of our input values. And what I want to do first is to apply a d value of a 4. And so I want to put that 4 as a multiplication factor right in with x. And so my parent graph this time is my square root function. And in order to multiply a 4 right in with that x, then we'll put it under the square root function. Now if we take a look at the effect on the graph of that transformation, I don't think I can make that smaller. We have our parent function with the square root graph right here, and if we put a 4 inside my square root function, we get this resulting graph. If I take a look at my favorite 5 dots there and see where they went, sure enough, putting a 4 inside my square root has a horizontal effect. Instead of going out 16 with that input value of 16 and going up by 4, we have an input value of 4. It is 1/4 of what it was. So my x coordinate, my 16, got divided by my d value of 4. Similarly here, I am over 9 in a horizontal aspect, and so 9 divided by 4 is a little over 2. So we were horizontally compressed to 1/4 of what we were. not horizontally 4, but only horizontally 1. And here where I have horizontal distance of 1, I go back to a quarter. A quarter of 0 is still 0, and so we have our domain and range isn't changed. And that point is what's called invariant. Even though we apply a transformation, it stays put in the same position. And so we've got an effect here where we can count on this horizontal aspect when we put a value inside my function, inside my square root. Let's draw what occurred. Instead of going over 16 in a horizontal manner, we only went over a quarter of that. Instead of going over 9, 9 divided by 4 is a little more than 2. Instead of over 4, it's a quarter of that. A quarter of 1, quarter of 0 is still 0, and so we got this transformed function. That is my function where I have a 4 inside my square root function. And so the result, we got a horizontal compression to a quarter of what it originally was horizontally. All right, what if we put a half inside my function? So pick a function. All right, I picked this square root function. And if I put a half inside my square root, or we could represent it by a 0.5, then let's take a peek at what occurs with that graph. And so we've got our square root function. Let's get rid of our horizontally compressed function. And this time, let's put, oh goodness, I think I put a third in here. A half is what I wanted, so let's correct this. We have got a third inside this function, so let's put a half. And so, those of you who are predicting what's occurring, there we go. So you can see that our, our horizontal distance here, instead of being a horizontal distance of over 9, I have come over 18 with that graph. Instead of a horizontal distance of 4, we now have a transformed horizontal distance of 8. Instead of a horizontal distance of 1, we've got a horizontal distance of 2. This horizontal distance of 16 is way off my graph. It was doubled horizontally. So let's take a look at that. My horizontal distance of 9 going out to 18. My horizontal distance of 4 being horizontally expanded to 8. Horizontal distance of 1 doubling out to 2. And a 0 still remains at 0. And so just like the parabola last day, when I was to put a multiplication factor inside my function, inside with x, we get the opposite of what we think might occur. Putting a half in there, you would think perhaps it would half the horizontal distances, but it always does the opposite of what we think it should. And so we get a horizontal expansion to twice as big. So expansion by 2, twice as big. So let's take our last look at what occurs with my rational function. Pull this up. Okay, we have our rational function here, and we want to put a 2 inside my rational function and a third inside my rational function. Now, what does that look like? Well, if we pick our function as a 1 over x, then putting a 2 inside my function, inside with x, would mean that I'm putting it inside the denominator, along with x. Excuse me. And so let's take a peek here at our rational function. Back this up a bit. There is my base graph, my parent function, my rational function here. And if I put a, what is it that I've put in here? A 2 Okay, so a 2 goes into the denominator, and horizontally, take a look at where my favorite dots went. Horizontally, instead of being over 1, that horizontal distance gets chopped in half, horizontal distance in half. And in fact, every horizontal distance is half of what it was. And so, just like our parabola, just like our square root graph, our radical graph, we can count on the fact that when we have a multiplication factor inside our function, we get a horizontal effect. This horizontal distance of 1 doubles out to 2. This horizontal distance of a half would double out to 1, and we get a horizontal expansion by a factor of 2. Sorry, horizontal compression. Oh my goodness, I'm thinking ahead here and I'm messing up. We saw that that horizontal distance went in half. I apologize. So we saw that that horizontal distance with a 2 inside the function goes to half of what it was, half of what it was, half all the way through here, half of those larger distances, and we'll head out there. We still share that asymptote where we will approach 0 but never meet it. Same thing here, my horizontal distance of 1 will go in half, horizontal distance will go in half, all in half. So a horizontal compression to half of what it originally was with its horizontal distances. Finally, putting a third inside my denominator. Now this becomes a little bit tricky in terms of trying to figure out what this equation might be. I guess technically what we're doing is putting a third inside my denominator. But then that means that I am dividing by a third. And we know that we never divide by a third. We would invert and multiply. So my 1 over x would invert and multiply with a 3 over 1. And so I would have a resulting equation of a 3 over x. And we saw that as a vertical stretch factor before. And so it's quite odd to have a horizontal effect that would stay as a fraction in the denominator, but I want you to know that it is consistent with our trend. We would probably not talk about putting a third in the denominator. We would likely present it as a 3 up top, as a vertical stretch factor of 3. But let's just take a look at the results on our graph and assure ourselves that this horizontal third is going to behave in a consistent manner. And so let's turn this compression off. If I put a third in the denominator, we get this effect. And sure enough, we get a horizontal expansion. So here, horizontally, I was at a distance of 1. Now I'm out at a distance of 3 in the negatives. It tripled the horizontal distance. It also, if you look here, that 3 over x version of my equation, I had a vertical distance of down 1, and that got tripled. And so a horizontal expansion is also the same as a vertical expansion here in this case. But when we're talking about horizontal, we can count on the fact that if you're working with a third inside your function, it is going to cause a tripling of your horizontal distances. All right, let's finish this up with our conclusion. Well, first of all, we have a horizontal expansion with a third. So horizontal expansion by 3 times bigger with a third in our D position. So as a conclusion, last day we concluded that an A value multiplying in front resulted in a vertical stretch factor, and now a d value multiplying inside any function, doesn't matter what function we pick, causes a horizontal stretch factor. Now remember, technically in math, a stretch can be an expansion or a compression. If d is bigger than 1, so if d is a 2, if d is a 4, if d is a 3, we saw that that caused a horizontal compression. Horizontal always does the opposite of what we think. Horizontal compression. If our d value was a fractional value, then that caused a horizontal expansion. By a factor, oh, we should say factor of d. I should change that. All right, down here for any function, we're going to learn a calculation method of where to calculate where my new transform dots went, especially when my transformations get crazy in terms of multiple numbers inside my equation. For any function, the graph of my function with a d value in it is obtained by multiplying dividing, oh, seriously, folks, I apologize, dividing the x coordinates of each of the points by the d value. What does that mean? Well, let's take a peek back up here and remind ourselves that here, when I had my f at x function, let's look at this particular point, if I had a d value of 4, I would look at that horizontal coordinate, that x coordinate, and it wouldn't be at 9, it would be 9 divided by my d value. 9 divided by 4 is 2 and a bit. My x coordinate here is 16. 16 divided by 4 takes it back to its transformed position and of the horizontal compression. So we're always dividing by that d value. So my point, any point on the original parent function, can be found with taking your x coordinate, your horizontal coordinate, dividing by the horizontal stretch factor, and the vertical stretch factor is not affected. Now last day I had asked you to see whether you could be successful with some of these graphs, so let's take a peek at these. Here I have my parabola, so my base graph, my parent function is my quadratic x squared. If I'm asked to put a 3 in front of my function as a multiplication factor, and I've chosen the quadratic, then my transformed function would be 3 times my x squared. State the transformations. Well, we've found out that the a value, the multiplication factor out front, is a vertical expansion by 3. And so every one of these vertical values gets tripled. So tripling a 9 would be way up at 27 off my graph. Tripling this 4 would take it to 12. Tripling a 1 would take it to 3. Tripling a 1 here. Oh, tripling a 0 stays at 0. And again, tripling the 4 to 3. We're off my graph for the rest of them. And a nice smooth curve through there. And this is the graph of a vertically expanded quadratic function. With my square root function, if we have a 3 inside my square root, here we're working with the base graph of a radical function, square root function. Putting a 3 inside means that I tuck the 3 inside my function with x. We learned that that's a horizontal stretch factor, horizontal transformation, which means that I have a horizontal effect always does the opposite. So instead of getting 3 times bigger, which you would expect with a 3, it gets 3 times smaller. So we get a horizontal compression to a third of what it was, because my horizontal distances get divided by that 3. And so 16 divided by 3. Well, 16 divided by 3 would be just a little over 5, 5 1/3, 16 thirds. So we would come out here to 5 1/3 and go back to a third of what that horizontal distance was. We've got a nice 9 divided by a 3, going back to a third of what it was. 4 divided by 3 is 4 thirds, which is 1 1/3. A 1 divided by 3, taking it back to a third, and so we get this horizontal compression a third of the way back. So we've got a 3x, whereas this is just our f at x is equal to x. Always remember to label when you have more than one graph on a line. All right, taking a peek here, our base graph, we've got our parabola. Our scale is different on this grid. We only went out to 5 here. We're going out to 10, which is why our base graph looks different. But that is our f at x is equal to our regular quadratic function. And I'm being asked to put a third inside my quadratic function. So my base graph, my parent function is my quadratic. Putting a third, a multiplication factor, inside my quadratic, we can see that it looks like this as a function. A horizontal function, I would think that it would be horizontally going to a third of what it was, but it does the opposite because it's a horizontal effect. And I know it's horizontal because it's inside my square, inside my function, a horizontal. Now, if I put a third in there, it means that I'm going to take all of my x values and divide by a third. Well, I never divide by a third. I would invert and multiply. And so all of my x values will triple out. I'll get a horizontal expansion by 3. And so here I have a horizontal distance of 3. I'll triple that out to 9. Horizontal distance of 2, triple it out to 6. Horizontal distance of 1, tripling it to 3. Triple a 0 is still 0. And then we should have a symmetrical curve over here, horizontal distance of -3. If I multiply that by 3, I go out to -9. And this one will become -6. This one will become -3. And we get an overall horizontal expansion 3 times wider than it originally was. Okay, one last transformation of our radical function. If I put a half out front, my radical function has a base equation of f at x is equal to x squared. If I was to put that a value out front, a half, it simply tucks in front of my square root equation. State the transformation. Well, I know that a multiplication factor outside my function is a vertical effect. It's an a value, and the vertical coordinate is affected, so my y's will change. That's a vertical, and the a value of a half behaves. You would think it should go to a half, and it does. So we get a vertical compression to a half of what it was. And so with an a value, I look to the vertical distances. Here I have a vertical distance of 4. I go halfway back. Vertical distance of 3, halfway back. 2, halfway, halfway. Half of 0 is still 0, so that point is invariant. And I get my f at x is equal to a half as a vertical stretch factor, creating a compression to half of what it was. Okay, taking a look at my radical function. Hopefully you had no troubles with this one. My base graph here, f at x, is equal to 1 over x. If I have a multiplication factor out front of 2, then I could state my equation as a 2 in front of 1 over x, or I could multiply that 2 in the top. You'll see that as well. Because it's an a value, it is a vertical transformation. It is a multiplication factor outside of my function, where my x's have the function input value going in the denominator. So an a value of 2 causes a vertical expansion by 2. And so I look at my function, taking its vertical values and expanding twice as big. Here I'm only up half, so I'll double that, and I get this curve that is twice as big vertically. So doubling, double that half, double that distance. I'm just doubling them visually. Now it's important to put in our asymptotes. We approach this value of 0 still, and approach this value of 0 still. There is my f at x being a 2 in front of 1 over x. And finally, my last radical function graph with a half inside. I have a base graph of 1 over x. Half inside would technically mean I have a half in here inside my denominator. We know that a horizontal stretch factor has a opposite effect. It's not going halfway horizontally, it's actually going to double. So we get a horizontal expansion. Dividing any of our x values by a half, we would invert and multiply, and we would make them twice as big. And so taking a look at my horizontal distances this time, a horizontal distance of 1 will go out twice as big with my expansion, horizontal distance of a half. And you can see that a horizontal compression, a vertical expansion is the same as a horizontal expansion in terms of these graphs. And so we can actually send a line into an identical position with different transformations, putting values inside or outside my equation. And remember, if we were to invert and multiply that half, we'd have 1 over x times a 2 over 1, and we would get this resulting same equation. So it's hopefully not too much of a stretch to show that we get a different transformation sending our radical function to the same spot. Okay, let's take a look. Hopefully you had some success with some of those on your own. Let's take a look at each of these. For each of the following, write the equation, state the transformations, draw both the base graph and the transformed function. So we have got a base graph. We're told to work with a quadratic, a parabola. I am asked not just an a value, but also to consider a d value. And so my transformed equation, if I am going to choose a quadratic equation, I want to multiply in front of my function. So I'll have a 2 out front. And then inside my square, inside my function, I will put that 3. Now we didn't do this in grade 10, mostly because you can square that value out and consider getting a 9 times a 2 being an 18 transformation with just a vertical stretch to land the same line in the same spot. But I do want to think about them independently because we're going to get to a point with a bunch of different base graphs where we will be considering our horizontal and our vertical influences separately. So state the transformation. Well, I know that an a value of 2 causes a vertical expansion by 2. And I know that a d value of 3, that affects my horizontal coordinates. And I will be dividing all of my horizontal coordinates by that d value to cause a horizontal compression. To a third of what it was, because dividing by 3, we go to a third of what it was. Now, if I draw my base graph of my quadratic, I've been doing a lot of those, so I am hoping that, you know what, I'm drawing too many quartics with my grade 12s. Over 1, up 1, over 2, up 4 for a quadratic, over 3, up 9. So with this scale, I get a fairly wide base graph. Okay, so there's my base graph. And I often call this the dance of the dots because we are just going to visually accomplish each of these transformations separately. So if I want to know where does this dot go, I'm going to vertically expand it by 2. So I'm going to double its vertical distance. So instead of up 9, it will be at up 18. Then I'll look at this one independently. I want to horizontally compress that horizontal distance to 1/3 of what it was. Take that over 3 and divide it by the 3. And so this dot is vertically expanded and horizontally compressed, and I am done with it. This one is a vertical distance of 4, so let's vertically expand that by a factor of 2, so we'll go up to 8. It is a horizontal distance of over 2, and I want to chop that in 3s. And so I could do it visually, say, oh, well, that's about 3, and go back to here. Or I can say my x value is 2, and I'm going to divide that 2 by my d value of 3, and 2 divided by 3 goes back to 2/3. And so there is my 2/3 as an input coordinate. This, and that one's done. This coordinate, where does it go? Well, if I double that vertical distance up to from 1 up to 2, and then I will take this horizontal distance and go back to 1/3 of what it was. If I double a 0 or take 1/3 of a 0, I'm still in the same spot. And so we get this set of transformed dots where we're vertically expanding and horizontally compressing. And we will get the same symmetry, double it and take it 1/3 of the way back, double it vertically, 1/3 horizontally, double it vertically, 1/3 horizontally. And so I can apply both a vertical and a horizontal stretch factor. I can double vertically and take it to 1/3 horizontally by compressing it. All right, let's take a look at the next graph, and we will transform a radical function, a square root function. So let's draw that base graph. Hopefully these are taking you no time at all to get the proper base graph down. All right, let's look at our transformations. I want a 3 in front of my radical function, multiply a 3 in front of my f at x, and I want a half inside my f at x. Well, with an a value of 3, I know that that is, again, a vertical expansion. However, with a d value of a half, dividing those x coordinates by a half will invert and multiply, and we will make them bigger. We will get a horizontal expansion. So we're going to get bigger in both dimensions. Horizontal expansion by 2. We'll double it. We'll double our horizontal distances. So if I take this vertical distance of 3, I surely can triple that. Up to 3 times 3 would be 9. I'd be a little off my graph. But if I took that horizontal distance of 9 and doubled it, I'm off my graph. So we're not going to be able to accurately transform this dot. So let's go to this next one. I have a vertical distance of 2. I want to triple that 2, so we'll be up to 6. And I want to look at the horizontal distance of 4, and I want to double that horizontal distance out to 8. And so we'll have this dot being transformed over here. Similarly, my over one, up one, I was a little lazy with that base graph line going through there, but we will have a vertical distance of 1 tripling up to 3, and a horizontal distance of 1 doubling out to 2. And so I will have my 2 transform dots that will still stay on my grid. Multiplying, my 0 still remains at 0, and so I am able to show this transformed function where I have a vertical stretch factor by a factor of 3 and a horizontal vertical expansion and a horizontal expansion by a factor of 2. Finally, we have got our rational function to take a look at here. Another function where I can have an a value and a d value. If I was to put these inside and take a look at where those dots go, I would be looking at putting a 2 out in front of my rational function and a third inside. Now I certainly can simplify that. I would invert and multiply this 1/3 to be a 3 over x, and we could multiply the 2 and the 3 to get a 6 over x, and we could achieve the same transformations with a single vertical stretch factor of 6, but I want to show you how we can independently think about them, because later on that will become important. But with an a value of 2, we get a vertical expansion by 2, and if we have a d value of a third, we get a horizontal tripling, a horizontal expansion by 3. Okay, now I'm not going to draw the base graph on this particular graph, mostly just because it gets too crazy. Remember, we have our asymptotes at x equals 0 and y equals 0. And multiplication factors do not change the value of 0. So unless we're shifting up, down, or unless we're shifting left, right, which was the stuff of the day before yesterday, then those asymptotes are going to stay in the same spot with our vertical and our horizontal stretch factors. So let's put those in and we'll know what our values will be approaching, where our line will be snuggling up. And normally my base graph would have an over 1, up 1. If I put a 1 input in my denominator of my parent function, I would have a 1 output. So I want to vertically expand that by a factor of 2. Vertically. So I will vertically double that distance. So instead of being up 1, I'll double it. And then I want to horizontally triple its horizontal distance. So my horizontal distance of over 1 will go out triple. And I could put more dots on to be more accurate, but honestly, as long as you land that one for me, I will be happy. Finally, over here, our last dot, we will go back 1, down 1 normally, but I'm going to vertically expand that. Double a -1 would be -2. That won't be its final resting position because I also have this horizontal expansion. Instead of horizontally 1, I will be horizontally out 3, and we'll head up a nice smooth curve heading towards our asymptotes, and we can draw our transform function. I'm going to leave this one until the next day. We'll start our lesson by referring to this, and then tomorrow we're going to be actually combining all of our transformations, all of our up, down, left, right, stretching, compressing, and we'll actually see what it takes in an equation to reflect our base graphs. But now what I want you to do is to take out your, oh, this is not it. We had a sketching sheet. We'll get that handed out. And of course I can't easily find it. Here it is. All right, sketching functions. What I would like you to do, and you need to work on this independently, but you may check with each other. We have simple transformations where we're putting values inside our function, putting values in front of our function. And so what I would like for you to do is to be practicing sketching these. Check your sketches with each other. There's a bit of a different kind of question here. We have our base graph here. Label the base graph. And if these are my transformed dots, then find me a transformed equation. On the back, again, recognizing how to draw or craft our transformed equation. Let's perhaps do one together. We can do the first one. If I have a 2 in front, then I would pick a function. The function I've chosen is my quadratic function. We put a 2 in there. My quadratic function, I'm multiplying a 2 in front. This is a vertical, not a horizontal stretch factor. We get an expansion, not a compression. and we get a factor of 2 as our expansion factor. So circle what applies, cross out what doesn't, and when we have multiple stretch factors, then make sure you touch those separately. So finish this up for homework. Be ready for a check your understanding question at the beginning of our period next day, where we will be combining a couple of transformations, and we'll be moving on from there to do combinations of transformations, where we will not only stretch and compress, but we will shift up, down, left, and right as well. Thanks so much, guys. We'll see you soon.